Today, in this talk, I want to give you a glimpse into the kitchen of my PhD thesis. And in this kitchen, over the past 4 years, I've been preparing all kinds of recipes, as you can see on the right-hand side, which is on the cover of my thesis. So what you see here, for example, are these chocolate Tetris bars, which in fact are the partitions in the title. And by a certain procedure, here depicted by this whisk, these partitions got mixed and they end up being this delicious quasi-modular form. So we go from partitions to modular forms. And in fact, there's a whole story related to this, started with the work of the Dutch physicist Robert Dijkgraaf in string theory. And this problem in string theory he was studying was quickly afterwards being translated into the world of enumerative geometry, which is the first field of mathematics which occurs in my thesis. And there's a second field of mathematics we will be seeing today, and this is algebraic combinatorics. And for example, these are the partitions. They are living in this field of mathematics. And then lastly, there's number theory, as you can see from the occurrence of the modular form. So now I will explain what all these things are. And let me start by taking a look into partitions. So if you have into recipe. So if you have a certain recipe, for example, a recipe for cake, then you have certain ingredients. But you also need to specify how much you take of each ingredient. And once you've done that, there's a certain way of preparing to end up with this nice cake, nice bread, or as we will be doing today, to end up with this nice quasi-modular form. And what will be the ingredients for us? For us, the ingredients, as I said, are the partitions, and we will see later how to choose which are the right amounts of each partitions to take. But let's first let me explain what are partitions. I will start with an example. For example, this 3 plus 1 plus 1, this is a partition of the integer 5. Why? Well, because these are integers, positive integers, which add up to 5. And even so, for example, this one, 2 plus 1 plus 1 plus 1, this is also a partition of 5. So in general, a partition of some integer n is a way of writing this integer as a sum of positive integers. And we do not care about the order of summation. So in fact, with this definition, one can easily find out that these are all partitions of the integer 5. What I've also done is I've made the connection with the chocolate Tetris bars you saw in the beginning. So if you go back to this partition, then I've here depicted 3 boxes for the first 3, then here 1 for the second number there, and then here 1 for the last 1. So this is a Young diagram, as it is typically called, of the partition 3 plus 1 plus 1. And also for the other partitions, in the same way we can depict all the corresponding Young diagrams as I've been doing here. So these are all partitions of the integer 5 with the corresponding Young diagrams. Okay, and if we have for each integer a certain amount of things, in this case partitions, then it's always wise to consider the corresponding generating series, as we are doing here in this result. So what are we doing? We are summing here over the set of all partitions for all positive or non-negative integers. And here we have the integer that the partition lambda, where we are summing over, is a partition of. So to be more concrete, you see here, for example, the number 7 and corresponding to the power 5. So this means that if you are taking partitions of 5, there are 7 in total, as we already know by now, because these are 7 in total, 7 partitions of 5. But we can also see, for example, that there of the integer 2, there are two partitions. This is what you see here in this generating series. And then we have here an equality, which is due to Euler, that you can write this generating series as this infinite product. So this means that if you consider this as a formal power series in Q, as we are doing here, and you take down the Taylor expansion of this infinite product, then you will end up with this generating series of partitions. Okay, so far so good. We have seen the ingredients of our recipe. Now let's take a look into how much we take of each partition. So for this, we use the symmetric functions. So symmetric functions occur in many domains in mathematics, but for us here, the domain of the function will be the set of all partitions, and we define this symmetric function just by taking the sum of all the parts of the partition, but no, not sum together, but after raising each part to the power k. So for example, if we take k to be 3 here, and we take the partition 2 plus 1, which is a partition of 5, then we get here 2 to the power 3, 2 to the power 3 plus 1, and this is 17. This is just the value of this function, which has the interpretation of the amount of partitions of these partitions we have to take in the recipe if we take this function for the amounts. But then also another example is given by as 1. So here we k to be 1, then we just add up all the parts of your partition, and then this is just this number which was being defined as the integer that lambda was a partition of. So if we are making a recipe with this function, then of the empty partition we take no, we don't take it. Then of this partition consisting of only one part, we take 1. Then these two partitions, then the value of this function is 2. And then for these 3, etc., etc. So now we have a description of all the ingredients and how much we take of each ingredient. So then the next question is, what is this whisk? How do we mix these partitions in order to get some output, some result in the end, which in fact will be a modular form? Okay, we do this by taking the Q bracket. So this is the mathematical equivalent notion of the whisk. And we have the Q bracket of a certain function. For this function, you should just think of these functions or these symmetric functions we saw and defined before. And then we define the Q bracket of f to be some formal power series in the variable q. Okay, and then this is the definition. So let's take a look at what I've written here. So in the denominator, I have this generating series, which we already saw before. This is something we know because we have the result by Euler to express this. We have a formula for this. And here there's something new because it's, again, we are summing over all partitions and we have this factor there, but now we also include the value of the function at the partition lambda. And if we do so, then, as I said, we will get some formal power series. So let's consider an example again. So here we take the function as 1, the same function as on the previous slide. So recall this is just the sum of all the parts of all partitions. So just by plugging this into the formula, we will get this expression for the Q bracket of S1. And then if we expand, we will get the coefficients 1, 3, 4, 7, 6, etc. for the in the power series occurring. If you are a number theorist, you will directly recognize, this is the divisor sum, which are being taken here as coefficients. So we are adding all divisors of the integer, and which is the power of q, the exponent of q. And in fact, this generating series is the first example of a quasi-modular form we will be seeing today. So now we already see that if we start with the function S1, the final result will be a quasi-modular form, and we have entered the realm of number theory. So let me say something about quasi-modular forms. Quasi-modular forms are everywhere in mathematics. To mention a few instances, for example, they occur in Fermat's last theory. In fact, not in the statement, but they are really necessary in the proof of Fermat's last theorem. They occur in the same way in the proof of the sphere packing problem in dimension 8 and 24. More recently was this being proven, and more related to the work in my thesis, they also occur as certain generating series corresponding to coverings of tori. So these coverings of tori is the problem in enumerative geometry I was talking about in the beginning, which also had an analog in string theory. And by fixing a torus here and here another Riemann surface, and by countering how many ways we can define covering maps, then the generating series of this procedure in the end will be a nice quasi-modular form. So this is another instance where quasi-modular forms do occur naturally. And I won't be defining quasi-modular forms today, but I will state two key properties of quasi-modular forms. And the first is that you can add quasi-modular forms, you can take differences, products, and with all these operations, the result, if you started with quasi-modular forms, is a quasi-modular form. And what you even can do is you can take derivatives of quasi-modular forms. Quasi-modular forms are certain functions which emit derivatives. And by doing so, the derivative, again, is a quasi-modular form. Okay, so this is the first property. And then the second one is that, in fact, you can start with only one quasi-modular form to generate all of them using these procedures. So by taking sums, difference, and products. So you can, by iteratively doing that, and also important, you have also to take derivatives. If you do all these things, then you, in fact, need only one quasi-modular forms. And this one quasi-modular form is the one quasi-modular form I already showed you, the one with as coefficients the divisor sums. So this is what the final result will be. But before I will now say more about how to, about this final result, let me take a look into what happens if you apply these natural operation on quasi-modular forms in the context of recipes. So, for example, let's just consider what happens if you have the sum, or if you add all the ingredients of two recipes. In our example, cake and bread, and you add all the ingredients. So points-wise, so there's here 200 gram butter, here there's no butter. So if we add this, we get 200 grams of butter. And here with the salt, 1 gram of salt, 1 gram, so this will be 2 grams of salt. If you do this, where you first had cake and bread, you will get something which is a bit in the middle. I would call it cake bread, and probably this is quite like the bread the Americans used to eat, like to eat. Okay, this is what you have if you add recipes, and you can also do this for our recipes, because if you start with the function s1 and the function s3, you get two recipes. And then if you add the ingredient and you use the Q bracket as the whisk for the ingredients of the points-wise sum, you will get another quasi-modular form. So we can add the functions which gives the weights to all partitions, and then we will still get a quasi-modular form. Okay, now we go further and we go to multiplication. So if you have all the ingredients of cake and all the ingredients of bread, you take the points-wise multiplication. So 200 gram butter times no butter is no butter. And then 200 gram self-rising flours times 200 grams self-rising flours is 40,000 grams squared of self-rising flour. And then also 1 gram squared of salt. This doesn't really have a meaning. And also it doesn't seem like there will be a nice recipe which makes this into a delicious something to eat. It doesn't work. But then the surprising thing is, for our functions, it does. Because if we start with the function s1 and then go to the function s3 and you multiply all these numbers, so 3 times 9 is 27, and you do this for all the partitions, what you will find is that not only these functions have quasi-modular forms as the Q bracket, but you will even get for the product that these functions are quasi-modular forms. And this is a very surprising observation, given that you do not expect this to hold for arbitrary recipes, for like the recipe with cake and bread. So this is the observation which I make now, that not only the Q bracket of S1, but also its squares, its and of S3 squared, S5 squared, and S7 squared. These are all quasi-modular forms. And but even other combinations, S1 times S3, or threefold products, or things like this. It doesn't really matter which products you take. Any polynomial, in fact, in these functions, in this symmetric functions, will give rise to quasi-modular forms. So I've written here the more like the mathematical explanation why this is something you would not expect, namely, phrased more mathematically, the Q bracket is a linear mapping, so this is corresponding to adding, but it's not a ring homomorphism. So you would not expect it to behave nicely under products. But in fact, the result, which this is the main result of today, and one of the results in my thesis, is that for all functions in the algebra of the symmetric function, so let me stop a bit to explain you the word algebra. This just means a space where you can add, as in a vector space, and where you can multiply, as in a ring. So this is an algebra. So this result says that for all polynomials in these functions sk, the Q bracket, so the result of this procedure with the whisk will be a nice quasi-modular form. A very surprising result, if you would have to ask me. And what is in fact even more surprising is that it's not the only such example, but there's also another such algebra, which goes really back to the work of Robert Dijkgraaf in string theory, but then was later generalized by Bloch and Okunkov. And this other algebra has also the property that for all functions in this algebra, the Q bracket is a quasi-modular form. So this is very surprising, and it's really asked for an explanation how it can be that although the Q bracket is not a ring homomorphism, you still have that for certain algebra, for all elements in this algebra, the Q bracket is always a quasi-modular form. How can it be that such a result exists? And in fact, this is one of the questions I answer in my thesis, and there is a truly wonderful explanation for this, which makes use of convolution products. But with Pierre de Fermat, I'm afraid I have to say it doesn't fit in the margin of this talk and also on the slide anymore. But don't worry, it's really in my thesis, so you can read it there. But for now, I will end here by saying that we have a recipe, which I'm considering in my thesis, which starts with partitions, and by a certain procedure with the whisk, the Q bracket, in fact, you get quasi-modular form, these nice functions. So you go from partitions to modular forms. And what is special about this is that these recipes are not only stable under addition, as all good recipes should be, but they are even stable under multiplication. And this, I think, is a truly delightful result.